So what we just brought you to is Cs50 Spaces.
Oh, wait, back up. Welcome to section.
Welcome to section!
Yay!
Super section!
I'm Allie, and that's Rob. Okay, now we'll explain spaces.
So what we just brought you to is Cs50 Spaces. You'll be using this a lot in your sections this semester. Basically, like, we've already had you download the appliance, and you can think of Cs50 Spaces as like a web interface talking to an appliance that we have on some server somewhere. So you can run your code in this interface, and we'll see how to do things. You can also look at the code of other people in the section, and
as some people have found out, you can chat people on the side, and we'll all see it too, so that's exciting. Come on in, come and sit, take a seat.
So
no,
sections
you guys can come. Oh.
Sections are going to be much more interactive this semester.
Oh, he's like, oh. Okay, cool. So if you guys are just coming in, you can go to this link, if I can get there, right here.
Could try it.
We can't really write it because there's a board space, but this link right here, go to that on your computers, and you'll enter your Cs50 Spaces, which is a pretty cool thing. Okay. Do you have a problem?
Yeah, so you can find the problems. Now you need to be able to write this somewhere. So if you go to cs50.net/psets, and this is the Hacker Super section. So if you go into the Hacker edition of pset 1 and look at the specification, somewhere down on page...
So basically, while Rob's looking, what we're going to do in section today is there is a section of problems
on page
called
8.
a section of problems.
Section of questions.
Sorry, a section of questions, and those are what we're going to go over. Those are what we're going to go over today in section, and we're going to code it on Cs50 Spaces, and hopefully that will work, and we can just talk through them, and you guys can ask questions whenever you feel.
Yeah, so this is going to be a common thing with most psets. I think with this one, it says you don't have to hand these questions in. But the idea is that these questions are put on the pset, and you can come to section to have those questions answered. Or if you don't come to section, you can answer them on your own or get help at office hours or something. But these are questions that are supposed to prep you for the problem set. And on the Hacker Edition, a lot of the questions might just be like about expanding your current CS knowledge.
Yep, pretty much. OK, so is everyone on Cs50 Spaces? Hi, come in. Yes, of course.
Yeah, this will be easier once you are actually in your sections and your TF can just email you the URL beforehand.
Yay, take a seat. There's seats here. The front isn't that bad. What? So Cs50 Spaces, we're getting there. Does anyone have any questions before we get into what?
There's not even any chalk. I could try to fit it in.
Sorry. You can use your fingernails? We're in a very low-tech room for a very high-tech class. OK, is everyone kind of good? Does anyone have still questions about it? As I said before, we're going to go through the pset specs, the section of questions and the pset specifications. And so there's just a couple problems that we're going to code up in Cs50 Spaces. So is everyone good? OK, good.
Do you have a laptop?
You can hang out with Lucas. He's sitting right next to you. Bonding time. OK.
Okay, so start with the first problem?
Yeah, we can start. Do you want me to? I can go. All right, so we'll go to the pset specs. Oh, why is it
Control.
So... OK, so are we going to answer these things as well?
Oh, yeah. So...
Oh, did everyone watch Rob's starring shorts? OK, cool.
So, yeah, I don't think we necessarily expected you to have watched it before coming to this section, but we can discuss those problems beforehand since they are under the section of questions things. So if you haven't watched it, don't worry. Those who have can try and answer. So the first question, what is a preprocessor? How does hash include cs50.h relate? So does anyone have an answer for that?
He doesn't like talk it out. Sure, go ahead.
Hash includes cs50.h is some pre-written code, and instead of copying and pasting it in your program, by just saying include it, the preprocessor knows that it's there and that it should add it in later or before anything else happens.
Yeah, awesome, cool.
So when you're actually compiling a program, the preprocessor is this first step. Compilation happens in like 4 big steps. So the preprocessor is the first big one, and it's this guy that goes through and looks for all of these hash symbols. And any line that begins with a hash, the preprocessor looks at and sees if it can process it. So hash include cs50.h tells the preprocessor to look for some cs50.h file and just copy and paste its contents into this file. So you can really hash include anything you want, but it's mostly going to be .h files. We have not gotten a hash define yet, so that doesn't matter.
Yeah, we're good on that one. All right, does anyone have any questions about that? Are we good? Next question.
In the short, there's like something about .c as well. Is that relevant or is that irrelevant?
About .c with the preprocessor?
Yeah. Or did I make something up?
Oh, so the short might have been showing me pre-processing this file and outputting it to another .c file. So like you can pre-process this file. You can, when you just run like make hello or clang hello .c, you are doing all compilation in one big step. But you can explicitly do it into its separate steps. So like first you can pre-process it, and then you can compile, then you can assemble, and then you can link. We'll get to those other ones. But pre-processing, you kind of pre-process it, and then it goes into another .c file. Because pre-processing doesn't really change anything. It's just a bunch of copy and pasting. You could manually copy and paste it yourself.
Oh, okay.
And to be clear, the .c file is a C file, so it's written in C code.
Oh,
So that's kind of, it's going from C code to C code. You're just adding more code with the pound.
When you've pre-processed it, it's still a valid C file.
Okay.
Good question. I like that. Okay. Next question.
So it'll be,
what's a compiler? Anyone? Yes.
It changes the preprocessed code into assembly.
Perfect.
Yeah.
Cool.
So that's what the compiler is doing specifically when we're using Clang. In a very general sense, a compiler is just like taking code in one language and turning it into another language. So in C, or well, Clang is taking code that's in C and transforming it to assembly. And you don't have to be able to understand the assembly at all, but that's the language that it's turning it into.
Okay, and then what's an assembler? Anyone? Yeah. Sorry, what?
Yep.
Yes.
So the assembler, now, like assembly code is really, really close to what your computer can understand. But remember that it doesn't quite understand the text that is assembly code. You need to convert it into straight ones and zeros. So it's like a direct translation process. We could just give you a table that maps what each assembly instruction means. But the assembler is just doing this translation for you. It's transforming the assembly code into ones and zeros.
Okay, and then for the last one, what's a linker and how does -L CS50 relate? Anyone?
So this is the hardest and least explained one in the compiler video.
Does anyone remember like seeing -L CS50 in like a command?
It's in the make. Yeah.
It's in the make.
After you run make.
Yeah, cool. Okay. Is there any guesses or like vague remember? Yes, go.
I mean, I'm not sure, but short was like really crazy, but was it something about like doing like separate files with each library and then like putting them all together in one library?
Yes. So when you have like hello.c is a really simple program, you're really only doing like one thing in it. But when you get into other programs, and I guess even when you use getString in your programs, you need to start including other files. So the Cs50 library is one such file in which we have the implementations of getString and getInt and all of those things. So what the linker does is it goes around looking through all of these files, seeing where functions are defined, making sure that when I call getString somewhere, it knows that getString means that it's the getString over in the Cs50 library. So the linker just takes all of these files, smashes them together, and now you have an executable.
So keep in mind if you're using the CS50 library, you need both the hash include cs50.h at the top, and then also in your make command, as you said, you have to have the -l cs50. So you can't just have one. So that's just something to keep in mind for future.
So let's say there's like another library, like cs51.h, then we'd also have to add like -l cs51.
So the only reason this -l cs50 works perfectly because we have that set up in a specific place in your appliances so that it knows what -l cs50 means. We could just give you a cs50.c file, and then you could compile it saying like clang hello.c, cs50.c, and then it would make your executable by putting those two files together. It knows that -l cs50 means some cs50.c over in some directory that we specified in your appliances. So if you wanted a cs51.c to be specifiable by just saying -l cs51, then we would also need to put it in that directory so it knows where to look for it.
What was your question?
Yeah, why do you have to link the CS50 file if wasn't it copy paste at the first step when you pre-processed it?
Do you want to take it?
Sure. So the cs50.h file is separate from the cs50.c file. Have you gotten to like function prototypes in class? Okay. So basically, the cs50.h file is just going to copy and paste.
Do you guys know what signatures are? Okay, so pretty much if you look at...
Let's pretend cs50.h is not there. Now, this file, you're doing string s equals get string, but when we've gotten to this point in the code, it has no idea what get string is. It knows it's a function since you're calling it, but it doesn't know that it's actually supposed to return a string. So, like if I said string s equals get int, this doesn't make any sense since you're assigning an integer to a string, but it doesn't know that get string does make sense because it doesn't know that get string returns a string. So what cs50.h says is something like this.
So what Rob is typing is it's a promise in a way that it's going to have this function called getString.
So this is all that cs50.h is copying and pasting in here, as well as getInt and all those things. And this just says that getString does return a string. You don't know how it's implemented yet, but when we get to this line, now it knows that it correctly returns a string. Yeah.
So if we didn't bother with the include cs50.h thing, instead just wrote the prototype for the ones that we were actually going to use.
Yeah, so let's run this.
Does it? So it by default will do the -l to cs50 just because you programmed it?
Expression. Oh, so
Yes, because it's in the make, as you said, it's in the make command. It's in the make file.
cs50.h also happens to type def char star to string. You can completely ignore what that means for now, but that is also something included in cs50.h. So now things worked perfectly fine. It runs exactly the same as it was when we just had the hash include cs50.h. And so including cs50.h happens to over-include things you need. Like you don't use getInt in this program, but it doesn't matter. It'll just ignore it.
And then when you do the -l cs50 over here and like right here, what's going on is that it's having the actual implementable code. So that's where it actually is doing this, writing the code for getString. So it's not just the promise anymore. It is actually like going through and taking the string and all that stuff. Make sense? Questions? All right, cool beans.
Now we can move on to actual code.
Okay, so here's the first problem. So it says, write a program that prompts the user for a lowercase letter and then converts it to uppercase without using bitwise operations, as per the sample output below. So you can see you run the program with the ./a.out, and then you're going to put in lowercase a, and then your program should give out capital A. So why don't you guys all give it a shot on CS50 Spaces? So you guys can all go here And you can delete all the code in here. And then you can go ahead and start coding the thing.
You'll probably want to use get char. That's included in the CS50 library.
Yeah, I guess it might be better if you save the top part. So you might want to like just change the step in the middle. So yeah, go ahead and work. Feel free to work with each other.
And you can ask questions if you
What's
have.
a bitwise operator?
So ignore that for
Don't
this
worry about
problem.
it. If you don't know it, that's good.
We're
That
going to
means-
use it in the next problem, but if you don't know what a bitwise operator is, that's fine.
Is that like turning it to ASCII code? No.
No,
No.
that you can do that for this problem.
How do you do that?
So, if only I had somewhere to write,
Or something to write with.
I could just kind of type into this.
Type at the top.
Oh, I'm sitting on a mic. So, we saw in lecture that like the ASCII value for capital A is 65, and capital B will be 66, and so on. So you can literally use quote A quote to mean the number 65. Like this is the value 65. I can do something like int x equals 100 minus quote A, and now x will have the value 100 minus 65.
You can run that and show that. Oh, maybe not. Never
I have
mind.
to print it. So
So then
you
how do you turn it back to character?
So if you
Can
don't,
you like char?
you just
something?
force
So,
it to be char
I could
A
yeah, it's
equals.
char. So there's the distinction between a char and an integer is just in terms of size. So an integer happens to be able to represent things up to like 4 billion. A char is only able to represent things up to 255. But there is no difference between them other than this. So you can say char C equals 65, and that's equivalent to saying char C equals quote A.
Oh.
This, yeah.
Oh no, it doesn't actually save things.
No, you can't do that.
That's just
Zoom out. Okay, so what Ali just wrote was a program which first prints 100 minus quote A as an integer, which was 35 as we expect because 100 minus the ASCII value of A is 65. Then she prints it, but now using %C, which means interpret it as a char. So 100 minus A is 35. Interpreting that as a character happens to be the hash symbol. If you look at ASCIItable.com or whatever, you'll see that 35 is the hash symbol.
Okay, any other clarifications about the problem? Okay, you guys can go ahead and do it then. Feel free to like ask questions or talk to each other. Or if you're already done, you can relax.
Did they just say in class that all the like lowercase letters are in order and also the uppercase are also in order? Because that's something useful for the problem.
Good point, Lucas.
Yeah.
So, did you guys all get that?
Yes.
Okay.
How you do it, right?
Yeah.
Yeah.
The amount of spacing and so on.
All right.
What is the question asking? Just convert to.
Convert the lowercase to the uppercase. That's it.
Okay.
Yeah. Yeah. I think that's it.
Should we write it? Or I guess we'll just look at someone else's. Oh, just give him.
So, for those who might be stuck, a way, if I have some char C, and let's say it happens to be the letter D. So now, how can I figure out what letter of the alphabet C is? Like, not D, but I mean like D happens to be the 4th letter of the alphabet. And if we start counting from 0, then it's the 3rd letter of the alphabet. So if A is 0, B is 1, C is 2, D is 3, how can I figure out in position what position of the alphabet C is in? Does anyone have any ideas? What?
What about the first one?
So wherever A is, subtract whatever.
Yeah.
Yeah, awesome. So you could do capital D. Oh, sorry. You take the character and you subtract the first one, as you say.
So if
Sweet.
D is something like 68, and we subtract A, which is 65, then we get 3 telling us that D is the third letter of the alphabet, starting from 0. So you can use that. Now we know what letter of the alphabet in terms of capital letters, or we can do the same thing for lowercase letters to figure out what lowercase position we're in. And we can use that to then convert that to uppercase using a very similar idea. Ask for suggestions.
Do you guys, wait, are you guys, I don't know how far you guys are. Are you, most of you done? Are you still working? Are you stuck? You guys can just shout out. Stuck. One person's stuck. Cool. I tend to be stuck too. Are you
done.
You're done? Okay.
This
Done.
lowercase, uppercase.
Yeah. Cool. Are you checking that it's in lowercase form? Okay, cool. Well, I don't know. What are other people? Did this hint help you as for like unsticking yourself?
Not really. I mean, but just because, I don't know, I'm not digesting it yet.
Okay, cool. Do you want to try
Well-
or do you want to go and talk?
What I was going to say is, so using this, do you understand how we got what position of the alphabet the letter is in?
Okay, so when you put things in like single quotation, a single quotation.
Yeah.
That returns a number. That's like.
Yes. It will be translated to the ASCII value it represents. So
Okay.
do you want to go to ASCII table, whatever it is?
Just like one of these?
Yep. So when you put any of these symbols,
No,
ignoring a lot
point
of the,
on-
using the cursor.
Yeah.
I
That's
see.
exciting.
So ignoring these ones on the left, which are special symbols.
Just zoom into just this.
If you put any of these symbols in single quotes, then it will be translated to this value on the left.
This is like the decimal number for it. So like A matches with 65, B to 66, and you'll note that they're all in order, like alphabetical order, which makes a difference. So as Rob says, like before in that code piece, we were calculating kind of the distance from the first letter per se. And so and that'll be the same whether it's uppercase or lowercase.
So when we did D 68 minus A 65, we get 3 because D is 3 positions into the alphabet.
So then how would you translate that over to find the little d? Is what
Yeah,
we're finding.
so if I have 3 now, I know I want to go 3 letters into we happen to be going lowercase now, but let's say I want to go 3 positions into the lowercase side of things. So how can I do that? I know lowercase a is 97, so how do I find 3 positions into the lowercase letters?
Wait, so I have one more question actually.
Yeah.
Yeah, go ahead.
So for this, it doesn't really matter if I know which positions. Like I don't need this table actually.
Nope. You will never need to use any of these numbers. And this is an important point in your programs, that you should never hard code any of these constants. Use single quote A, single quote. Never use 65 or 97.
Those are called magic numbers, and they're really confusing. Like when you're debugging your code, you might not remember what you used them for, and for us grading your code, we won't really know what you're using them for. So it's better if you actually use the characters, so it makes more sense to people. Okay, any other questions? Are more people done or unstuck? I guess we can check. It's really creepy that you can just see people's code.
Yeah. We don't have to do that here. We don't know people's names either.
Oh yeah, well that makes it better, so then we're even more unbiased when it comes to just randomly picking someone. Don't worry, I won't do it. If you have random things about, never mind. Okay, how are people doing?
So the 9th line should print out a character.
Yes.
Yeah, so if you go down,
Oh, can't do that.
you'll see that it printed the hash symbol.
Oh, okay.
We can
I
have
guess
it.
another way you can look at things is we're printing 2 characters. First one we're printing is the letter A. The next one we're printing is just 65. It'll probably yell at me for these. So if we just run this, notice that it prints A both times. because we're asking it the same thing. We're asking it to print the letter A, and then we're asking it to print the number 65 interpreted as a character, which is the same thing.
Do you have something to say? Oh, just kidding. Sorry. All right. How are people?
We can just walk through it.
All right. Okay. So how do you start? Anyone? As a hint, we have to get something from the people, like from the typers. Oh yeah, a prompt. Perfect. So we'll type. What do we type? Anyone? Or should I just type it? Are we actually typing the?
Sure.
All right. So we'll type a printf to prompt it, so it can be like, give me a character. Okay, and then what? Why is it doing?
I don't know.
Okay. Okay, so now we're telling them to give us a character, but then how do you actually get that character?
Use a string, maybe?
Get string? Get car? Okay, so what's the difference between a string and a car?
Strings are a series, like an array of characters.
Cool, yeah. So in this problem, we only need to consider one character at a time, so we're only going to do get car for that instance. So we'll
We could implement a function if we wanted that took an entire string and went over the string and like changed all lowercase to uppercase and all uppercase to lowercase. But here we're just asking for one character.
So now we like have the character, but then we need to save it. So then we'll add car C. What?
Define a variable.
Yeah,
Mm-hmm.
exactly. Okay, so we have our character.
I think you might be. Yeah, you're only 3 spaces in, which is why it's yelling at you.
Okay, cool. Now that we have tabbing set, what happens next? What's the next step?
So what our program should do is change a lowercase letter to an uppercase letter. What if I happen to enter the hash symbol?
It's a good symbol. I've used it a lot.
Is that a valid thing that I can convert to an uppercase form?
No. Right, so we should check that. So we can have an if statement checking. So if the C is greater than or equal to the lowercase a. So then if you look at the chart, you'll notice that it has to be between here at 97 in the lowercase a, and it can be any of these, and it increments all the way down, and then there's z at 122, and so it has to fall between these two values. Does that make sense?
So if C is not between 97 and 122, or you should never need to use those numbers, if C is not between single quote lowercase a single quote and single quote lowercase z single quote, then it wasn't a valid character for us to uppercase.
So in code form, we say that if C is greater than or equal to single case, lowercase, wow, how did you say that? Okay, is greater than or equal to the lowercase a, and it has to be above the lowercase z, right? So it has to be less than or equal to lowercase z. So we're making sure it's between the two. Then we can continue on with our happy code. What?
Oh, so I figured we would just keep asking if we happen to not have a lowercase letter.
Oh, I wasn't aware of that. Oh, sorry. Okay, so if we were going to do as Rob says and make sure that we can keep asking them, then what should we do?
Yeah, we should use some sort of loop, because the user can enter something invalid an untold amount of times. So you can use a while loop. The purpose of a do-while loop, literally the only time in your entire lives you will ever use do-while loops, is when you are asking for user input. So the fact that we're asking for user input here is a hint that we should use a do-while loop. And why is that? Because do-while loop always happens at least once. So when you're asking for user input, you want to have that to happen at least once, and then if things were successful, you can keep going. If not, go back and ask again.
So in other words, we have the do section, and so this is telling it to do something. So printf, so like print the statement, the prompt, and also get the character, or attempt to get a character. And then we have to check if it actually did it correctly. So then we add the conditions, then we say while, and then we have the conditional statement.
But now we have reversed the train of thought, and that we originally were saying if C is in this range, it is valid. Now you want to reverse that and say if C is not in this range, then we need to go back and do things again.
Oh yeah.
So while this is not true, we want to go back and ask for another character. Does everyone see that? Questions on this? Okay, so now we have a valid character that we can uppercase.
So then what? So then what's the next step for uppercasing it?
Add 32.
You add, sorry, what?
Can't you just add 32 to the number?
So yes,
So if you
not in terms of magic numbers. You should only be using single quote stuff.
Okay. Well,
But you can get
so how
32.
did you get the number 32? I guess is what we're saying.
uh,
So we can come up with the number 32 together. And
Minus big N.
yeah, but if we're going to do it in the two steps we kind of did before with the position stuff, so the position in the alphabet that C happens to be is C minus lowercase a. So if we enter the lowercase d, position is going to be 3. And now we want to take things to the uppercase range of things. So now our new C is going to be the capital A plus position. So do people see how that brings us where, like, we're moving from the lowercase range, the exact depth we were into that range, and going down into the uppercase range and going that far into it again, which is going to be the same character, but now uppercased.
And for the people that were confused by how he just said 32, basically he combined both of these into one statement. So like an equivalent way of writing this is to say, you can just kind of substitute position, the C minus A, and just put it right here. So what he did, okay, char new C equals uppercase A plus C minus lowercase a. And then like, because of algebra, you can like move them around, right? So then you can also say that you can move it around, so char new C equals uppercase A minus lowercase a plus C. And this, if you'll notice, if we go back to the chart, so we have uppercase A is 65 and lowercase a is 97, and so 65 minus 97 is negative 32. Hi, take a seat. Oh, you're used. You can sit right here. Cool. Okay, awesome. Welcome to section. So you'll notice that the difference is 32, and so that's kind of where he got that number. But it's not, as Rob says, the best way to do it because it has the weird magic number confusion.
Yeah. So you should use capital A minus lowercase a. You should not use just straight 32. So why should you not use 32? It's
so like if we did it, it would be like char new C equals negative 32 plus C. And like if you don't see any of the rest of it, like if this is all gone and you just see this single line, then how do you know what the negative 32 is? It's kind of just out of place.
So this is not, like, your program would work completely fine. It's just a style thing that, like, someone going in and reading your code, they're like, what does this 32 mean? Maybe they don't, I probably would not immediately realize that 32 happens to be the difference between a lowercase letter and an uppercase letter, although we're going to use that fact in the next problem. So 32 is, like, you could leave a comment above it saying, like, 32 is the difference between A and A. But at that point, why not just use A and you don't need the comment then?
It's just this way, the ways above it are a lot cleaner and style-wise. And so since you're just starting programming, or I guess not, since you're hacker edition. Never mind. But it's just a good way to just have, it's better to have better style. It's easier for other people to read.
You should never need to remember the ASCII table ever. You should just be able to use the single quote characters.
Everyone
Questions?
good?
Okay, so the next problem is substantial. So the next problem asks us,
The next problem is asking for us to do the same thing, but to use bitwise operators.
and of course we have not seen bitwise operators yet, so we will now discuss those.
Be excited, they're super fun.
So the regular operators, like x plus y minus times divide.
You type it in this. Okay, keep going.
There's also mod if you haven't seen it, which is you can use by the % symbol. But we won't use those for this problem. We want to use bitwise operators. Now remember, we brought it up in lecture 1. I'm not sure if we've discussed binary beyond that, but remember that every single number is represented, well, everything is represented in ones and zeros in binary. So, that means that, like, when I say the number 8, I happen to know that that's like 1, 0, 0, 0. What bitwise operators let us do is operate on these bits directly. So like now I'm no longer dealing in terms of 8, I'm dealing in terms of 1, 0, 0, 0, and I want to do things with those individual bits. So Ali has written the bitwise operators here. Let's actually, yeah, let's, like the number 8 we'll use as one of our example numbers, and that the binary representation is 1, 0, 0, 0. We'll use another number, 5. Actually, let's use 9 and 5. And the 5's binary representation is 0, 0, 0, 1, 0, 1.
Is everyone good on that? The binary stuff? It was from first lecture, I think.
So even if you aren't entirely on top of how to convert things to binary, that's not entirely important for this problem. We'll be using it, but like you'll have many more chances to figure out how to quickly turn things into binary. So using 9 and 5, now we have our bitwise operators. Oh, and also 9 and 5, like if it's in an integer, then really it's 32 bits, which means we have like 0, 0, 0, 0 a lot of times, then 1, 0, 0, 1 on the very end. That's just because no matter what you do, an integer is 32 bits. Just because we only need 4 bits to represent 9 doesn't mean we're not using up the other 27 bits for just zeros.
So just to clarify, one of these numbers that's a 0 or 1 is a bit. So like this one is 4 bits. And so Rob said that machines store them in 32, so then they would have 32 of either a 0 or a 1. Cool?
Okay, so now, the bitwise operators. The first ones we'll deal with, let's do and. So if we do 9 and 5. So what and does is, bit by bit, it compares the bits of the two numbers, and if both of the numbers are a 1, then it will return a 1. If one is a 0 and the other is a 1, or both are zeros, then it returns a 0. So you can think of it as like your logical and, like you need true and true to return true, but true and false is false. So it's the same thing, but now we're dealing with it with just bits.
So if you look at this, so you'll have 1, you'll line them up, so it'll be 1 and 0. And so do you guys think that would be, what would that evaluate to? Cool. No. Sorry. So does that make sense? So what is like the collective answer again? Sorry. So if you have 1 and 0, then what do you get?
So you just think of how you say and out loud. Like if you have 2 bits, x and y, you need x and y to be 1 in order for it to evaluate to true, or in order for it to evaluate to 1. If x or y are 0, then it evaluates to false, or 0.
It's good to remember also that 1 is true and 0 is false. So if you have like true and false, it's false. But then true and true, true and false and false.
So we have true and false. So then, so 1 and 0. So then again, sorry, one more time.
Would be 0.
Yeah,
Yeah.
cool. Okay, and then if we have 0 and 1, yeah. So you can always swap them in addition, and then if you have 0 and 0.
So it's 0. It's not that both numbers have to be the same. It's that both numbers need to be 1.
So both have to be true for it to be true. So that's 0. And then you have 1 and 1, which is?
Hey, these are pretty good numbers. I have all possible.
Good work. Wow. Wow. Okay, cool. So does that make sense to everyone?
So now we'll do OR. And this is going to be very similar. But now instead of x and y needing to be 1 in order for it to evaluate to 1, now it's just x or y need to be 1.
So 1 or 0 evaluates to, cool. Okay, 0 or 1 evaluates to, cool. And then 0 or 0, yeah. And then 1 or 1, cool. Okay, so that's like 2 bitwise operators. Awesome.
So now we'll do XOR.
Should we do all of them?
Yeah, because I think we're going to be using them all.
Okay,
oh
so
no, I guess we don't need to. But
so XOR works in that you have to have exactly 1 true and 1 false. So
XOR means exclusive OR. So now it's not if x and y are both 1s, it's now false. That is the difference between XOR and OR, is that OR you can have like if x is true or y is true, then we're good. No, XOR says if x is true, y must be false, or else it's not true. And do you have a question?
This is what's called the Lowercase.
yes, it's kind of similar.
Yeah, so when you get to like that low-level hardware stuff, these are the types of operations you're dealing with. Like at the hardware level, you will only deal with bits. You don't deal with numbers.
Okay, so for XOR, if you have 1 XOR 0, what should that evaluate to? Cool. If you have 0 XOR 1, cool. 0 XOR 0, cool. And then 1 XOR 1, cool. Awesome. Okay, cool. The next one.
I think these are all we have to deal with. We'll only do these.
No, they technically have to do.
Oh, that'll be for the last problem.
Wait, once again?
Yes. So, sorry, what was your question?
Can you explain the once again?
The XOR?
XOR?
Exclusive, yeah.
So the way the exclusive OR means is that there has to be exclusively one true and 1 false. So 1, 1, and 1, 0. Versus with OR, you can have, it just has to be, one of them has to be true or both of them can be true for it to evaluate to true.
So 0 and 0 would be false.
Right.
Yeah, but if you have 1 or 1, that would evaluate to true. But if you have 1 XOR 1, as we did, that evaluates to false because it's not exclusively 1 is true.
And this may or may not be helpful, but notice that the XOR is equal to just taking the OR minus the AND. And you can actually think of it this way, like XOR is just ORing everything together, but taking out any of the bits where both were true. So AND returns everything where both were true, OR returns everything where one or both were true. So subtracting that out from the OR gives you the XOR.
Any questions? This was a lot of information. Everyone good?
We can go over the next ones for the next problem / what time is it? Yeah, they won't need this until the next problem.
I thought it was this one.
Yeah. It is not.
You sure?
Yes.
All right, so
I'm positive.
why don't we start doing the problem? So the problem is, again, to change it from lowercase to uppercase, and this time to use bitwise operators.
So let's start with the binary representation of A, capital A, which is 65. So in binary, I'll center myself. So capital A is equal to 65, which is equal to, in binary, I'm going to mess up the number of zeros, that.
So does that make sense to everyone? So like
Is that true?
1,
Okay.
no 2s, no 4s, no 8s, no 30s, so
Yeah, well, okay.
no 16s, no 32s, and then 164.
Yeah, I think
it
that's
was
one
off
too many
by
zeros.
Sorry.
Okay.
Okay,
So we have the 64 set, then we have the 1 set, and combining those together, we get 65.
Cool beans?
So now, lowercase a, notice 97. What is the difference between 97 and 65?
You flip this section.
Yeah. So it's 32, which is its own bit. So that's going to be 1, 1, 0, 0, 0, 0, 1. And this is going to be true for all possible characters. So if we think of D, which is going to be 68, and that's going to be 1, 0, 0, 0, 1, 1. And then lowercase d is going to be 68 plus 32, which is 100, which is going to be the same thing that this was, but just flipping the 32 again. So 1, 1, 0, 0, 0, 1, 1, 1. So the difference between an uppercase and lowercase letter is just flipping that 32-bit position.
Isn't it 1001000 for D? No, wasn't the
Wait, it's 100, something I did wrong. This was not true.
it's a,
68,
it should be 4.
It should be
4 and then
I was thinking that it was a difference of 3, so then I just stuck the binary 3 on the end. This should be right.
Thank you. Good for pointing that out. That was sharp. All right. Is that clear to people?
The difference between the uppercase and lowercase version is always just going to be 32, and so it's always going to be a single bit that needs to be flipped to change between the two.
So in that case, knowing the difference between the capital A and the lowercase a is a good thing. Not in your code, but for like conceptual use. It's good. All right. So you guys can go ahead and code that in spaces now. Or should we just discuss it?
We can just discuss it. I don't know.
Well, you guys can try. Talk amongst yourself for a bit. We'll give you a chance to code it. That's cool. Yeah, we're just, just like telling the news, going through it.
And we're back.
It's kind of weird. I feel like we should have like a Cs50 news station and we can like actually sit like this.
Hacker news.
Hacker News 50. Feel free to ask any questions if you're confused.
Is anyone stuck?
Is anyone? Yeah, that's a big thing. Wait, are you like stuck in your chair? Oh.
No.
I was a little concerned.
Because I just realized that we are going to want another bitwise operator. For now, let's just convert uppercase to lowercase. So,
Oh, sorry. Did everyone get that announcement? We're going to go from uppercase to lowercase.
and then we'll discuss lowercase to uppercase right after that. Oh no. We have a bug in this, which I guess we never tried to run, which is just the char C needs to be declared outside of the loop because its scope is restricted in the loop.
In this case, is it wrong to use a number?
You don't need to. If I guaranteed you that capital A or lowercase a minus capital A was exactly 1 bit, but that you don't know it's 32, like things would work just as well if it were like the 16-bit that was flipped, or no, I guess it wouldn't, or the 64-bit were flipped, possibly. But so you shouldn't need to use 32. You can instead use lowercase a minus capital A.
What you can do if you feel like you're like writing too much is you can define it at the top. So you can be like int difference equals capital A or lowercase a minus capital A. And then you can like type difference instead. That's valid. But like just using the number 32 is kind of,
Even though it's because of the fact that it's the 32-bit?
yeah.
Like there could be the only guarantee we need to make you is that the difference between
my
lowercase and
gosh.
uppercase is 1 bit. It shouldn't matter that it happens to be the 32-bit that's flipped. For time considerations, we'll start going over this.
It's okay if you haven't finished. Don't worry about it.
So, assuming C is a capital letter, or we don't have to assume C is a capital letter. We know C is a capital letter after this while loop, do while loop. So that means it looks something like this A. And so if we want to bring this A to this A, what do we need to do? So how do we convert? We need to flip the bit.
Okay. How do we flip it?
So we know we want to flip the 32-bit. So that will do A minus A, or we could write 32, but darn it, it's the other way around.
Okay, so Rob here is calculating that number, magic number 32. So he's finding, where that bit flip area would be. And then what do we put where the question marks are?
How do we flip that bit? In terms of the uppercase letter, it is a 0, and we want it to become a 1. Yeah. That. So this is us saying we take A, we are ORing it with
Put it right below.
0, 1, 0, 0, 0, 0, and that equals that.
Does that make sense to everyone? You can go through it bit by bit if you want.
Are you allowed to use the minus sign?
Where's the minus sign?
Oh, you mean in here?
Oh, yeah.
So I guess this is us. We could say 32, and now we're just using bitwise operators. But
We don't like magic numbers. We're not going to do that. Also, I think it was just to use a bitwise operator.
If you use small a XOR a, will you get 32?
Yeah, I think.
yeah, you will.
This is how we would have done it for going from capital to lowercase. Now, can anyone tell me why why Rob and I changed the prompt and how we went from uppercase to lowercase instead of lowercase to uppercase as we did before? Does anyone have any ideas why that might be more difficult?
So we'd be,
Yeah, go ahead.
The OR operator was really good for adding.
Mm-hmm. Yeah, exactly.
So what we want to do in the lowercase to uppercase case is convert this A that.
What are you?
So we want to put in some numbers here and then use some operator so that it comes out to capital A. We're still probably using 32 somehow. But now, how do we get this to come out to this? So, actually, that should be fine.
What are you?
So C, oh, I still want that too.
So now if we're converting from lowercase to uppercase again, then we do the XOR operation, as you guys said. So
There are other ways you can do things. A lot of the bitwise operators end up being very easily definable in terms of other bitwise operators. So I was going to not use XOR at all, but XOR works perfectly fine.
cool. Okay, so we're gonna go to the last problem, which is to the last problem is to convert something into binary. So you if for instance you have 50 and then you convert it to binary, which is 110010. And so I think you guys all know about binary from lecture. And you also are not supposed to put any leading zeros into it.
You can ignore that part for now. The first pass, you can do it so that there are leading zeros, and then we can modify that to have no leading zeros.
Yeah.
If we have time.
So don't worry about that. So just try and get it in binary. a good place to start would be,
Need to ask for an integer.
oh yeah, that's a good one. We can start with that. So you can change the prompt. So instead of a character, now we're dealing with integers. Cool. Yes.
And now what is our do while condition going to be? So it's asking for a non-negative integer.
So when do we want to keep prompting the user for something else?
When it's smaller than 0.
Right.
So while I is less than 0.
Cool. Okay, and then now we want to convert it. Do you guys have any ideas of what to do? Any inklings?
Well,
Yeah.
they're-
Go ahead.
Do we have to convert it, or can we just print some zeros and ones? That would be the right number. Can you do a for loop and count up by powers of 2?
Yes. Yeah. So you don't need to convert I to its binary. The binary representation of I will not fit inside of I. You just need to print the binary representation of I.
In other words, you do not need to go by powers of 2.
Because like I is already being stored as binary, so you don't need to convert it to binary. Just go over its binary and print it. And you're going to need to use Bitwise because you want to look at the actual bits. Oh, I guess you don't need to use Bitwise, but please do. And that's actually, so you can just do powers of 2 by multiplying by 2. We'll go over one of the last two binary bitwise operators, which is this one. So when you take,
You have to both of them.
yeah, so let's go with 9. So 9, left shift 1. What left shift means is just move all the bits to the left and insert a 0. So we're moving all the bits of 9 to the left 1 position, which gives us,
Oh. Sorry.
yeah. So notice we have shifted everything left 1 and inserted a 0 on the right side. If we had shifted left by 2, we would shift everything left by 2 and insert 2 zeros to fill in the gaps. Question? Okay, so
And so then right shift does a similar thing. So if you have 9 right shift 1, then it's going, you're just moving everything over to the right, so you lose a digit, so 1 0 0 instead.
So it's fine that you are losing the bit that happened to be all the way to the right. There are different types of right shifts, but basically you can think of right shift as just dividing by 2, and you can think of left shift as multiplying by 2. So if you converted 9 shift 1, which was equal to 1 0 0 1 0, if you actually went through the binary and figured out what that was, it would just be 18. We just multiply by 2. 1 0 0 1 left shift 2 is going to be 36. We multiply by 4.
Makes more sense.
Yeah.
Okay, cool. So that's a handy bitwise operator for this one. Okay, so more confusion. Do you guys want to try it out? Or we can just jump right in and start it?
Should probably jump right in
Yeah, okay.
and walk through it together.
Yeah, okay. Well, I'll just go into it. So as he said in the beginning, we're going to just go through it bit by bit. So we're going to need a loop. Does anyone have an idea of the best kind of loop to go through this? We have while loops, do while loops, for loops.
So remember what I said before about we are only using do while loops to get user input. You will never pretty much ever use them for anything else.
The problem with do while loops is it does something before it checks for the condition. So it could do something bad and like hurt, do something that's not possible. So you want to check first.
There's a lot of cases like where you can use do while loops, but people don't expect you to use them unless it's user input. So we have used our do while loop to get I. Now, well, how many times is our loop going to want to loop? So we want to loop over each of the bits of I. How many bits are in I?
32.
Yeah.
So there are 32 bits. We don't want to say 32. We instead want to say size of which. Have you seen that in class yet?
Nope.
Oh, why does it say to use that? Size of int times 8.
So size of is like a
It's in source, it's in one of the source codes.
interesting. So size of is a built-in C function where it just tells you the number of bits in a
Bytes.
Sorry, the number of bytes that a variable has to store a value. So I think you went over in class that an int is 4 bytes. Maybe? Cool.
But you shouldn't need to know that an int is 4 bytes. You should be able to just say, or you should use size of int to get 4 bytes. And that's actually important for some things. An int might not be 4 bytes. On another computer, an int might be 8 bytes. And so your program won't work on that computer because you hard-coded 32 bits, when on that computer it happens to be 64 bits.
So we have like the total number of bits that you want to traverse.
And the difference between a byte and a bit is that there are 8 bits in a byte. So size of int returns 4 bytes. Then we have to multiply that by 8 to get 32 bits.
Okay, so we know the maximum, and we know we want to go through all of them. So we want to go from 0 to num bits. So does anyone know how to write the loop for that? Anyone? So we want to traverse the number I from the 0th bit to the 1st bit, the 2nd bit, the 3rd bit, all the way to num bits, like the max number of bits that you can get to.
What's the common loop we use when we want to do something x
4.
times? Yes.
Perfect. So we have 4, and then we'll create an iterator, which is not going to be named I.
J.
J equals 0, so we'll start at 0. And then we're going to have the condition to make sure while you're like going through it every single time.
More equal to num bits. Equal to num bits.
J.
J is less than num bits. So we don't want to do the actual equals one because they're num bits total, and we start at 0. So we're actually going to have the index is going to end at num bits.
We label the
minus
bits
1.
0 to 31. We don't label them 1 to 32.
And then we're going to increment each time by 1 because we want to check every single one. So we'll go J plus plus.
Why
So-
are you going through every bit?
So we want to go through every bit and like, oh darn it. So let's say we just have some number.
68.
We can use 68. So the binary is going to be 100100. So if this is inside of I, then we want to go over each of these bits. Is it a 1? Print 1. Is it a 0? Print 0. Then go on to the next bit. Is it a 1? Print 1. Is it a 0? Print 0.
Cool. Okay, so now we're at the correct index for where like that bit is. So how can we like check that specific one? So like let's say we're at J equals 0, so we want to check the 0 index the bit. So like in this case, this one. So now how would we like go about check? Oh, it would be this one.
Yeah.
Sorry. How would we go about checking that one, in a sense? Like, how would we check if it's a 0 or a 1?
All right. Well, let's. Yeah.
And? Yeah.
Yes. So let's say we already have 1, then this and this will return whether it was a 1 or a 0.
Cool. So we can go down. And we can do, as you guys said, of doing the and function. So we'll...
int, how do I want to say this? Is 1 is equal to I, and for the first bit we happen to be looking at, we're doing I and 1. Now, what are we going to want to and by for the second bit? Yeah, the second bit we're going to want to do 2.
So that'll be, you'll notice that the 1 has moved over to the left one. So have we learned any bitwise operators to do that function?
The next one.
Yeah, right, exactly. So it's a left shift. So instead of always checking with 1, we're going to shift it. And how many times are we going to shift it? So if we're checking the 0th one, then we're going to move it over 0. If we're, yeah, exactly. So you left shift it by j. Perfect. So now we know we have this int of if it's 1. And then, so Rob's kind of cheating here. And so now he's going ahead and he's just saying that if it actually is 1, because 1 evaluates to true, so we don't have to say like is 1 equals 1. So if is 1, then we print 1, and otherwise we print 0.
So our program has an overall bug. Well, questions on this first. Yeah.
Could you have put the is one inside the for like operation part, and then had it like ship itself as the last part? So is one equals 1,
Yes, you can.
and then
So we can actually show that once we fix the bug that I'm about to discuss with you all. So notice the order we're going over things. So given this binary representation, we are starting with the 0th bit. If it is a 0, then we are printing, or well, it is a 0, so we are printing 0. Then we go to the 2nd bit. It is a 0, so we print 0. Then we go to the 3rd bit. It is a 1, so we print 1.
So it's going backwards. So how do you guys suggest that we fix that and go the other way?
Yeah.
Yeah.
So instead of going from 0 to num bits, we'll go from num bits to 0.
So
Well,
for
num-
loops can always go the other way. So
Num bits minus 1, because
because
that's
it goes
the
from
last
0
number.
to 31. And then we'll always make sure that it's greater than 0, so you don't go too far to the right. And then you'll always subtract by 1 to go to the right.
So now we reverse the loop, and the number is back into printing in the correct way.
Don't you have to change the shift thing too?
No.
So no.
So we are we're doing the same exact operations except now in the reverse order. So instead of doing the shifting by num bits minus 1 to get whatever this bit is, instead of doing that last, we'll just do it first. And so by reversing this up here, we have reversed the order of everything that happens inside, but we don't want to change what happens inside at all.
Does that make sense? Processing. Okay, so does anyone else have any other conceptual questions?
Before we go into his point, which is
All right, we'll go.
instead of using J to be our, instead of using J to always shift by, like 1 left shift J, I think what you're saying is like
Oh yeah.
use J itself. So for J, I guess this is the hard one. J equals 1 left shift 31. Is that what I want? I think it's left shift 31. J is greater than or equal to 1. J right shift equals 1. I and J. So now instead of using, we are like,
You're constantly moving J instead of having an index to check it. It's not that bad. So we're using the similar kind of logic. So if you go back, oh, but it's going to lose it. Sorry. Okay, you're just going to type it again. So if you notice that like we have 1 left shift J amount of times, and we were incrementing J every single time by 1 increment. But this time, instead, they're doing that increment of J at the top inside the for loop. So instead of always moving it down,
so the very first iteration of the for loop, we have J is 1, 0, 0, 0, 0. The next iteration of the for loop, it's 0, 1, 0, 0, 0. I added something. The next iteration, it's that. And the 1 is just going to keep propagating down until we hit the very end, where now it's this. The next one, the 1 is going to be pushed off.
and then it
J
won't
is
be
no
1.
longer greater than or equal to 1. I could also put greater than 0, same difference. And then that's it. Questions? Yeah.
What's the right shift and equal? At the end of the
So that's the same as, have you seen like j plus equals 3. So this is the same as j equals j plus 3. You can do that for virtually any operator in C. So j right shift equals 3 is equal to j equals j right shift 3. You can do, so that works also with bitwise operators. And I should not have put 31 here. I should have put num bits minus 1.
Yay, no magic numbers. Okay, it's 4 o'clock though, so if you guys have to go. But does this make sense? Do you guys have any other questions? Yeah.
I was also going to throw in that if we wanted, has he discussed ternary operator at all?
No. It's okay.
So you could look into it for next time.
Okay, really?
Yes.
Now you're just showing off.
No, now it's, this is what gets people interested, and now
Yeah, you start
they'll
to-
go look into it. So now that does the same thing in one step. So we first check, is I and j 1? Is it true? If so, print a 1, else
Otherwise.
print a 0.
But doing it the other way is perfectly fine as well. It has the same logic. So it's not like one is...
And at this point, we can get rid of those curly braces because it's only one line for loop.
Okay, so does that make sense? Like, that was kind of a jump, but it was just kind of syntax more, so. Cool? Any other questions? No?
All right.
All right, cool. Thanks for coming to
Hooray.
section.